Good afternoon, everyone. I hope I am audible. Okay, so let us continue with the third lecture of the introduction series of GIS. In today's session, we will be discussing about the origin, definition, and the current state of how GIS is being used. So, first, we will have a quick review of where we are headed for now. So we are in week 3 and we are talking about different types of data and different types of model that is present with respect to GIS and how in the current form it is being used. We will quickly go through the summary of previous class so that we can brush up and discuss assignment 2 questions. So what we had learned in the previous class is about GIS information science and how it is used both as a software and a hardware to solve various problems. Spatial data, on the other hand, we defined it as a geographic information that can locate an object or phenomena on the ground. And with respect to that spatial data, there is a specific attribute data that is added information to the existing information of the spatial location. So suppose we have a specific data point on the surface of the earth, and with respect to that data point, there is going to be a specific attribute data that defines the spatial data. The relationships and indexing defines how attribute data interacts with spatial data. So we learned about these different relationships and how these indexings are done. We learned about the disciplines contributing to GIS, and in today's class we will be looking at more definitions and current state of GIS. So let us move on to the assignment 2 questions. So the first question was, which of the entity is not associated with the real world model? A. Relationships, B. Attributes, C. Geometry, and D. Type classification. So the answer was C. Geometry. This was already explained in the lectures of previous class, so you can refer to it. Question 2 asks, which of the following statements is all about ordinal data? A. An example of ordinal data value is classifying population growth as low, average, high. They can be kept in some natural sequence but do not allow any computation. They provide an identifier so that user can discriminate among different values. And D. None of the above. So the answer is C. They provide an identifier so that the user can discriminate among different values. So this statement is true for nominal value. The third question was, at least how many intersecting straight lines are required to create a polygon? A3, B5, C6, D, none of the above? So the answer was A. This is self-explanatory. As you understand, the smallest polygon or a polygon with the minimum number of sides is a triangle or a triangular based polygon. So the minimum number of lines that will be required to create this polygon is 3. Fourth, slope of a place is categorized as dash phenomena, discrete, static, fuzzy, continuous. So your answer is D, that is continuous, because data is treated as discrete when they are only found at a fixed location. So we can take a specific example of location of traffic signals only along a road. So the terrain of the region or at local or global scale is continuous, defining the height of the surface above the mean sea level, and slope is one of the factors defining the rate of change in the topography across space. The fifth question was, which of the following activity in a GIS routine is tedious and expensive? A. Data processing, B. Data collection, C. Data analysis, or D. Data manipulation. So your answer is B. Data collection. This is because data collection requires skilled professionals, so you have to hire them, and that accounts for nearly 15 to 50% of the total cost. It depends on your scale of data collection, it depends on the type of data you want to collect, it also depends on what is the level of professionals that you are hiring, so the cost will vary accordingly. Sixth, best way to define a road network is via point, polygon, pixels, line. This is very obvious, it will be a line. We have already understood this in the previous lectures. Seventh, data collection can also be referred as data storage, data acquisition, data pre-processing, or all of the above. So your answer is B, it is data acquisition, because you are acquiring the data. So it means collecting the data. Question 8. Starting point is not automatically the first in the line, but is instead randomly chosen within the list. This statement is true for stratified, systematic, random, or symmetric. So your answer here is C. This is self-explanatory again uh, from the previous lectures. So basically here we are talking about the type of sampling we will be doing or the type of data collection. So in terms of random sampling, what you do is you randomly select the first line, or you randomly chose in the list where you want to start from. But in a systematic one, what happens is that you've already created a defined starting point for your sampling or for your data collection. In terms of stratified, what happens is that you have a basis for random collection. Okay, so in a stratified data collection, we are actually doing a random sampling based on certain systems, based on certain criteria. For example, if I want to survey a particular geographic location for water usability, I'm going to select the areas that are located only near the existing water bodies. So yes, in that case, my criteria becomes the existing water bodies, but I randomly select the samples or the data that I want to collect from a particular line. Ninth, migration and housing data are examples of dash data: attribute, framework, topographic, socioeconomic. I think this is again very obvious, it's going to be socioeconomic, because migration and housing data consists of details such as number of people migrated from various places, including the age, sex, occupation, salary, etc. Whereas housing data includes type of building, number of people residing in the building, and other building amenities, etc. So these are basically qualities of social and economic type of data. The last question, undershoots, dangles, knots, switchbacks are all types of topological errors, scanning errors, geometric errors, inconsistency. So your answer here is A, which is topological errors that can be understood from previous class lectures. So for today's class, we are going to cover these four broad topics. First, we will be talking about origins of GIS and the timeline, how it evolved. Second, we are going to learn more about the definition of GIS. Then we will learn about the capabilities of GIS and the current state of art of how GIS is being utilized. So let's talk about the origin of GIS. So progress in the fields of computer technology, map making and photogrammetry led to the emergence of automated geographic information systems during the 1960s. So this has started already post independence in the 1960s. Notably in 1969, Ian McHugh introduced the concept of analyzing land suitability and capability through his publication Design and Nature. I have already recommended you all to go through McHugh's book Design with Nature. It is really, really recommended in terms of graphical representations, in terms of utilization of GIS, and how you can visually explain your graphs without writing too much of content about it. So, whatever maps or whatever graphics you are getting as an output of GIS, it should be self explanatory, even though you have to write text about it. So, on the right, the picture that you see is of Ian McHugh on the right, and this is his book Design with Nature, which is still so popular, even though we are way beyond 1969. Concurrently, the Harvard Laboratory for computer graphics played a pivotal role by creating a series of automated maps and analysis programs. So the first actual GIS, known as the Canada Geographic Information System, which is CGIS, was developed in the 1960s by Roger Tomlinson, primarily aimed at rehabilitating and enhancing Canada's agricultural lands. The momentum continued into the 1970s with commercial advancements in the field of GIS. So this is a rough evolution timeline of GIS. So here what we are actually trying to show in the evolution is the platform performance change. So how various platform and performance change due to the change in the platform of GIS. So initially in the 1982s we had ARC or Info, then it transformed into ArcView, Map Objects and ArcIMS. So these were mainly scripts, and these tightly scripted software were used with the help of codes, and they were requiring almost 10 times faster hardware. So, the processing actually demanded a lot of strong or very powerful hardwares, which were not really that efficient at that time. So, highlights of the evolution of S3 software from 1982 to present also took place parallel. In the second stage, we see that the scripts transform to objects. So here we had our GIS desktop 1999, which transformed into ArcGIS Server and ArcGIS Engine. Now this object relational software was two times uh, faster in processing, and this required 3.5 times faster hardware and better network connectivity. Then the scripts, after they transform to objects, they further transform to services. Once they transform to services, so this was the time period of 2008 to 2009 where ArcGIS actually came up, and REST API was also introduced. We had rich internet clients and mobile GIS was also there. So this service oriented architecture was two times faster in processing, but it required only 1.2 times faster hardware and improved networks. So as long as we are getting more efficient networks, we are requiring less faster hardware so that the load can be shared by these two efficacies. Finally, in what we have right now is now the scripts, objects, and services have transformed or evolution into cloud service. So in 2010 to 2014, we had an upgraded version of ArcGIS, and ArcGIS further went online. Then we had this imagery processing, and we also got ArcGIS as a platform. So it was not just there as a software, it also turned into a platform. So now we are using cloud computing and hardware virtualization. So technology drives the innovation, and this is how the performance changed based on the change of different types of hardware. Now, through different timelines, the invention of GIS is hard to pinpoint. Confluence of few pivotal events in 1962 and 1963 make it a good point in history to consider as the birth of GIS. So here, what we are seeing is that the first spatial analysis actually took place in 1832 to 1854, which was way older. So here, mainly the work started through the cholera epidemiology in Paris that was represented on the map. So I'm sure we all are aware of that epidemic. So the first time anything that was mapped like a spatial analysis was done for that epidemic in Paris in 1832. Next, we used paper map. So this transformed into a paper map that was used to geographically analyze the dependency of the cholera deaths in London in 1854. So this is how GIS actually kicked in. This is how the concept of GIS or the concept of spatial analysis came into uh, the usability of people. And then from 1962 onwards, we had various other processes going on. First, which we have already discussed, is Canada Land Inventory, which produced almost 1500 maps. So here paper was being used on computers to automate map analysis. Then it transformed or it evolution into a course that was taught by Edward Harwood as a computer handling and mapping of census data of Northwestern University. Then it further went to a laboratory for computer graphics. So now graphical interface was also introduced, and he started studying about Urban and Regional Information Systems Association, and it became an annual congress, which is now known as URISA GIS Pro. Then it moved further in 1968 as Geographic Information System by Roger Tomlinson. So finally, after a span of almost 100 years, 100 to 150 years, it transformed into Geographic Information System, this entire spatial analysis process. Then it moved further to being the first real demonstration of computer-generated maps. So from 1970, we actually started using computer-generated maps. We introduced open source GIS software based on Unix. Then we went to DOS. Then by 1990, we had other desktop solutions like RQ. We also used GIS software from Esri, Caris, MapInfo, and ADAS, and many more platforms. Then we went to Open Geospatial Consortium, and National Atlas of Canada was considered as the first online atlas that was released. And finally, in 2004, we had this OpenStreetMap and Google Map that came in, and now it is working pretty efficiently, and we have much more platforms apart from these. But this is how it kicked in and it started, and now it has evolved much higher. So I'm sure you've seen this timeline earlier also in Professor Bharat's presentation. So this is the basic timeline which we have taken from ResearchGate, and here again we are trying to show how GIS was created by Tomlinson, and then it evolved, how essay came into the play, and how uh, for the first 10 years it was just an introductory phase of the entire analysis software and platform, and eventually it went to experimental phase as soon as SA came in. After the experimental phase, we had the commercial phase where we founded the MapInfo, and we also introduced GPS systems. And after the commercial phase, we had the globalization phase from 1990 onwards, and it still goes on. So, for the current use, we can project a future of GIS which calls upon improvement based on certain parameters. Those parameters are GIS in the cloud, real-time GIS, web GIS, space-time, and augmented reality, which is actually being explored in almost every field now. So, what is exactly GIS? What are you referring to as GIS? So, whenever you're talking about GIS, you are talking about a system for capturing, storing, checking, integrating, manipulating, analyzing, and displaying data which are spatially referenced to the Earth. So, this was defined by Corley in 1987. GIS can also be defined as a system of hardware, software, and procedures which are designed to support, capture, manage, manipulate, analyze, model, and display of specific, spatially referenced data for solving complex problems and management of those problems. So this was David Cohen in 1989. And a working GIS, if you have known or if you have worked in the Navy, you will understand that there are five key components: hardware, software, data, people, and methods, which was defined by SE in 1997. And then automated systems for capture, storage, retrieval, analysis, and display of data, which was done by Clark in 1990. So all the definitions focus mainly on the data, the users, software, hardware, and methods. So what are we trying to understand here? If you look at this particular figure, you can understand that it all starts from a site selection. Okay, so this is your starting point. This is where you actually uh, start to choose where you want to perform the spatial analysis. So your first step is always going to be selection of your site. After you have selected your sites, you create your several analysis, or you categorize your analysis, that what are the several analysis that you are going to do. So it can be engineering design, and you can also go for demographic analysis. It could be topographical analysis, which is again also related to engineering design. You can have watershed analysis, which will help you create several resource inventories, because water is a resource. Again, land management, land is also a resource, so that will also add to your resource inventory. Then you have network analysis. So since we are constantly evolving and we are doing infrastructural development, analysis is one of the commonly used analysis, and it is also very critical. Then we have incident mapping, because definitely there is so much of climate change. There are natural and man-made hazards which is taking place globally. So it is important that you can map in different incidences. Then you have spatial measurements, because we utilize measurement for construction as well as for various other purposes, including agriculture. So spatial measurement is also an important aspect. Then you have corridor selection, that along which corridor and why along that particular corridor you want to perform a specific spatial analysis, so that you can understand the logistics routing. So logistic routing is again important, as it is related to your resource exploration, transportation modeling, as well as facility management. So ultimately what you are going to do is you will create a geoprocess model. So this geoprocess model helps or aids into different types of spread and diffusion that would be happening throughout the world. Then there are many different definitions of GIS, as different users stress different aspects of it. So let's take two examples. So first example is SV, how we defined it, which we have already discussed. So it is talking about a computer hardware, software, geographic data, personnel designed to efficiently capture, store, and manipulate, and also analyze and display the georeference information. And the second one is you also provide a simpler definition as computer system capable of holding and using data which is described on different locations on the surface of the earth. So what you are doing here, if you break down the word GIS, your G stands for your geographic reference, and your IS is your information system. So your geographic reference is related to the data of spatial coordinates on the surface of the Earth's location. So you are actually talking about the map, you get your specific location data. And when you are saying information system, that is the database of attribute data corresponding to the spatial data and procedures to provide information for decision making. So GIS is with information system with geographically reference data. A number of related data layers can represent many geographies for the real world. So if you just take this small example, it has land parcels, then it has districts, it has several streets, it has soil, it has utilities, like you can see there are industries, there is solid waste disposal, there are parks, and you also see certain river and discharge point into the river. Then you have land use, how there are different houses, there's a school, there is industry, and there is a recreational area. Then you have topography. So you can see there's a riverbed which has a lower topography, and then in the park, which is just adjacent to the river, it has a little higher, but the highest topography is where the housing is located. And finally, you have the hydrology. So hydrology is what is happening above the ground level. It is mainly a cycle, but actually, uh, it's more of a cycle that continues. So how water is being discharged, it goes up. Then there is a certain amount of precipitation, and then it comes back to the earth. Whether it recharges the aquifers or not, whether there is a flooding situation or there is a drought situation. So all of this is analyzed using the hydrological aspect of this particular map. So there are certain capabilities of GIS. So some of the capabilities which we listed. So we listed six of them. First is data capture or input of data. Second is management. Third is manipulation. Fourth is analysis. Fifth is modeling. And sixth is display or output of GIS capabilities. So first, let us discuss about the data capture or data input. So what is basically happening here? Here we are inputting data in several forms, including maps, satellite data, digital data, or tabular data. All of these data are utilized in different formats. So if you take map, you have to have a digital format of this data, which is also known as digitization. If it is a satellite data, you have a scan format. So digitized data is a vector format, whereas satellite data is a raster format. Then you have this particular digital aspect related to your map. So this and the tabular data both are represented in the form of either logos or table. So there are spatial tables for attribute data. So both of this is actually your spatial. This is your attribute. So this leads to your capture of data. So this is how you capture different forms of data from different sources so that you can spatially edit the data if required. You can reproject them, and then you can change the generalization and the layering if needed. Otherwise, you preserve them as it is. In the management section, it is seen that there are five different aspects that we have covered, but let us talk about the key points of GIS capabilities and its management. So in the management section, what are we actually talking about? We are talking about the linkage of attribute data to spatial objects, how we are linking these two variables. Then link to external databases. How we are linking external databases so that there can be proper utilization of whatever information is available apart from the database which we have. Then we also talk about making changes in the existing databases so that we can improve, modify, or upgrade them. Then there is updated database features. Then you have import and export from to other GIS or DBMS. What is a DBMS? DBMS is actually your database management systems. And the last one is to combine map sheets to create large databases match the edge of neighboring map sheets. So basically you combine different map sheets in smaller sections to combine and make it into a bigger one. So here what we are talking about in the five pillars of location intelligence. So this is a rough scheme of how data is being managed. So first you need to have a strategy, okay, just like you have in a business. So you must strategize whatever data you have or whatever database you are holding. Second is organization of the data. third is application of technology to that data, how you are utilizing the different tools, editing features and management features which are present in the GIS software. Third is maintaining a culture. Every database will have a certain factor innovation, so you need to maintain that. And last is your knowledge about your database. When you're saying literacy in terms of this particular context, it is actually your knowledge about the database that you acquire. So all five pillars of location intelligence is important when you are managing your GIS capabilities. Then you have manipulation. So what is happening in manipulation? You're actually changing the layers of your data. You're changing the crux of your data. So what you're doing here, you have, for example, if you take this particular example, so you have a mine site map, then you have a ventilation system map, you have sensor node location, you have emergency routes. What you do, you composite overlay everything in GIS so that you are able to measure the environmental attributes. You can also analyze the spatial data, you generate map queries, you develop your modeling, and then finally you can do your risk prediction. So the world remains as it is. How can we describe the geography is known as the data inventory. How this geography operates is your process models. How can we alter this geography is the capability or sustainability models. What are the alternative scenarios? You can always create different scenarios by designing or sketching, and you can say the world as it could be rather than as it is in the present scenario. Then what are the consequences of change? That is evaluation or analysis. So here you're talking about geo accounting. And finally, how should geography be changed? So you're taking decisions based on the values that you get from this entire cycle. Now we come to the fourth capability of GIS, which is analysis. So the first feature in analysis is query. What is it doing? It is actually selecting features by its attributes. So for example, let us say I have a certain data set and I want to find all the districts with literacy rates less than 60%. So what happens? The query feature of analyzing your spatial data will instantly categorize all the districts within my database that has literacy rate less than 60%. So select features by geographic relationships, find all the dental clinics within this district, right? So you can perform this also using the query. And the third example would be combined attribute or geographic queries. So find all villages within 10 kilometers of a health facility that have high child mortality. So what you are doing here, you are doing selection and measurement, you are doing an overlay analysis, you are doing neighborhood operations, and you are also doing a connectivity analysis. The second feature which we have within analysis is called buffer. So what buffer is going to do for you is buffer will find all the settlements that are more than 10 kilometers from a health clinic. This is just an example. So what is your buffer point here? Your buffer point is actually 10 kilometers. So from the 10 kilometer of a particular point, which is your health clinic, you are trying to find all the settlements. So it creates a buffer of 10 kilometers from your health clinic. The next feature is point and polygon operations. So here you are identifying for all villages into which vegetation zone they fall. So what happens is that you are trying to identify a specific point in a polygon. So my village becomes the polygon, but my vegetation zone becomes my point which I am trying to identify. Then you have your polygon overlay. So here we combine administrative records with health district data. So we are laying one data over the other. Geocoding or address matching will match an address list to the street map, and network operations will find the shortest route from village to hospital. This is just another example. So this tells you how we create different analysis in the segment using GIS. So if you're talking about, let's say, network operation, so this is how local networks are represented. Then if you're talking about, let's say, buffer, so let us say this was my so this is just an example of setback and bi-directional buffering. So what happens here is, suppose if this is my health clinic, as said in the example, if this is my health clinic, I'm actually saying that, okay, from the so this white section represents the outer wall of the health clinic, and let us say this is the boundary wall. So from the white space, which is the health clinic building, I'm saying that, okay, this bluish broad thick line represents my 10 kilometers buffer space, beyond which I'm trying to find for the settlements. Then this will be an example of a different uh, uh, overlay of layers. So it can be in terms of polygon of overlay. So this might represent different polygons, where one is your road network, the other polygons, the different lines, maybe they represent different degrees of heat effect which is created along this particular route at a specific distance. Next, we are talking about the modeling. So this is your fifth feature. So here what we are doing is, we are trying to identify or predict a process that has created or will create a certain spatial pattern. So in this we are talking about diffusion and interaction. So diffusion takes care of how is the epidemic spreading in the province. So if you use the diffusion feature, you can actually try to find out how a specific activity is spreading or it is evolving in a specific region or location given the boundary. Then, if you're talking about interaction, you are looking at where do people migrate to, how different anthropological movements are taking place. And if you consider the what if scenarios, you can also look at, if the stadium is to be built, what is the ideal location? How you categorize a specific location as the ideal location? You first have to go through certain parameters, and after you have set those parameters, you are going to fix your ideal location. So basically, it is a guiding surface. Extension considered the value on the surface to determine whether potential step is up or down across the surface. So whenever you are doing a model, you have different representations of it on different layers and different scales. So these two, so this is one figure, but it represents two different scenarios. So this is downhills from a road. This is how we see it in a 2D. This is how only the roads are appeared. This is how the downhill is represented. And finally, if we look at it in a 3D format, this is how it looks. So this is the final model that is created from GIS based on the terrain data and the network data. Similarly, if you look at this particular example, you see how ocean treated as a tilted plane. So you see ocean is treated as a tilted plane, and here we are going down current from a watershed. So the play here is of watershed, but the play here is that of roads. So these are just two different topographical and regional contexts where we are trying to show how your model is going to look like. Now we talk about GIS capabilities, display or output. So when you have created all the other analytical documentation and modeling parts, you get a final result, you get a final output. This is one of the most simplest output that you can get, which is composed of different lines that result in the formation of several polygons. So this, let us say, gives administrative boundaries of a certain geographic location. This again is a different kind of output. So what the user or the creator has done is that they have created different types of uh, GIF formats. They have actually created a time lapse of different years, and how the evolution of this entire bit form is taking place has been recorded based on the output that they have got from GIS. This is again another form of output where you can see that different built structures and their forms are defined with the help of various street divisions in a specific geographic location. This is another output. So here what is happening is that on a Google map or on a geographic base map which is derived from the internet, the user has tried to demarcate different administrative boundaries, including the administrative regions, the municipalities, the federal districts, and finally the country. This again is a different type of display or output that you can get. This specific model represents your digital elevation model where hill shades are taken into consideration and different values of contours or elevation values are also considered. This is again another form of output where you have a specific base map and you are trying to digitize the different build structures only to get a specific morphological aspect of a built-in map. This again is representing only the forest area. So what you have done is here you have done an analysis to do a specific kind of feature or data extraction and you have extracted only the forest area and their intensity through GIS. So how are we going to define GIS in planning and policy analysis? How we are going to talk about this? So we will just take a short 5 minutes break. It is 4:40 right now. I will be back at 4:45. Please be here. You may drink water or take a break. NPTEL. NPTEL. Okay, I hope I'm audible. So let's get back to where we were. We were talking about GIS and planning and policy analysis. So what happens here is that first we go to the real world and we collect our data. So based on our data resources, we have to maintain a certain data. So we have a database management system. Our data is inputted in that DBMS, and then we have a data retrieval or manipulation, after which we are able to perform our data analysis. Now we have information for decision making after we have analyzed the data that we had. So it is released to the users and action is taken in the real world. More about this, so we will understand this based on a small example. So let us again take another example from GIS maps, GIS and maps in disaster management. So what we are doing here is once we get the data, we have a certain so once we go through this process, what is going to happen? So we collect a certain data, we have a resource inventory, we have logistics planning, we have evacuation planning. So we are collecting data to get all of these. So we have a communications planning, we have a needs assessment, that what all will be needed in the preparedness of any kind of disaster management. But we can only come to the preparedness level once we have collected the data from previous disasters, from previous whatever disaster has taken place. We have collected the data, we have managed the data, we have analyzed everything, and then finally, when the time comes for decision making, this is what we end up doing. So we first do the preparedness level. After preparedness level, we have a recovery or rehabilitation stage. So here we do a spatial planning, we have infrastructure, we have housing, we have livelihood. So we consider everything collectively and we plan for rehabilitation from a disaster. Next, we have prevention and mitigation. So what happens here is that there is a scientific hazard analysis that we do. We have simulations and modeling of the area. We have the simulations and modeling of the disaster where it took place. Then we have vulnerability analysis. Then we have risk assessment and mapping. So we map several risks from which we can get a specific forecast. We get a specific result. We get to depict the future. So here we also have a stock assessment. Then we plan for the relief. Now here in the relief section, we are planning for the search and rescue. We look at different types, different scales of rubble and debris, how it can be removed. We have logistics. So logistics actually a part of every stage, because until and unless you don't have logistics, you will not be able to implement that on site or in the real world. Then we have delivery of relief supplies. We are now prioritizing our actions, because once you come to the relief section, that means the disaster has taken place and you have to have a plan to actually provide some sort of facility to the people who are getting affected by it, who are actually in that particular disaster zone, who are suffering, whose houses, whose uh, livelihoods are impacted from that particular disaster. Next, we have a response stage. So here we have a situation analysis. So what we do here is we analyze different situations and we try to create crisis maps. Here we also talk about information communication and evacuations and shelters, because after a particular disaster or after a particular vulnerable situation, there is a response stage where people are hitting back. So you need to have dispatching of resources, it needs to be equitable as well. You need to have early damage assessment so that no further damage can take place. So all of this is only possible when you are efficiently collecting the data in the disaster site, and you're also managing that data and analyzing them in the correct form within the time frame that you have, because it needs to be done really quickly but efficiently. And the final one which you have is prediction and warning. So here what you do is, once all of this is over, your response stage is gone, things are getting back to normal, there is a probability of hitting back. The disaster can come back in terms of floods, earthquakes, tsunamis, several others, even forest fires. There is a probability of hitting back. So what you do, you start monitoring. Then you forecast. Once you monitor, you analyze your monitoring, you forecast it. You send early warnings so that people are ready this time. And there is a scenario identification. So what could be done? So all of this is possible only if you use GIS and its mapping efficiently. So this is just one section, one segment, one field where you can actually utilize it and do something so productive and efficient for the manufacturer and as well as the flora fauna. Now, if I talk about the current state of art, so there are two sections in the current state of art that I can define. Uh, so there are not actually two, there are more. So let us start with these two. One is the high end, the other is the low end. In the high end, we are talking about integration of GIS and remote sensing. Then we are also incorporating interoperability, that is OpenGIS standards. Then we have advanced spatial analysis, scientific visualization, storing spatial data in database management systems. So all of this is high-end state of GIS. If I talk about low-end state, we have desktop mapping. Okay, then we have commercial data providers, we have GPS, we have mapping add-ons to spreadsheets, which is your Excel sheets. Then we have digital map libraries which are available online. We have access to spatial data via the internet. So this is how different high and low ends of the current state of affairs of GIS goes. Next, we have mobile and online platforms. So if you are considering mobile, with a smartphone you can do a lot. So everyone is a potential data center. We all have a specific data sensor with us, which is this mobile device that we use, right? The second is volunteer geographic information from each individual. Simple things, daily social media updates. These are very small things, but this is like a gateway for location associated information. If I am putting a post on Instagram, I'm actually sharing my location data. So I am adding to the database which is available to the servers, right? I am also sharing it with other users, knowingly, unknowingly. Then there is data analysis on site. So there's an asset management, field data collection, inspection, incident reporting with geotagged images, etc. Then you have real-time GIS plus mobile GIS, which equals to one distributed system architecture. So you can actually combine both of this together and you can combine the databases and you can use it more efficiently, because a lot of time it is not possible to collect all the real-time GIS data on your desktop. You need to have a mobile system, right? When you are talking about web or online platform, this consists of a server. So you have a GIS server and a client, which is your desktop application. This has several advantages. So it has a more global reach. There are large number of users because you can use it from the comfort of your homes. You have unified updates, you have diverse application, you have reduced costs, no installation of softwares, right? Then you have a better cross-platform capability. You find it easy to use and it's compatible with different web browsers. So you don't actually go through the hassle of going through an exe installation or an API installation or anything like that. You have customized dashboards and you have a much user-friendly uh, UI system of these particular dashboards. Now, this brings us to the end of this session. What can we see from here? What have we learned? So, we have learned the origins of GIS and timeline. So, GIS is evolving as strong subjective tool for all fields, and it's not that the evolution has stopped. It is still under process, okay, and it will keep going on as we bring artificial intelligence and augmented reality into the play. It may evolve beyond our thinking capabilities, and we yet to see what it can do with the database it has. Then GIS is a telescope, it is also a printer, a scanner, and a mapper. So it has a multi-purpose interdisciplinary role now, and it is being used in fields that we could not even think of when it was introduced. We have learned six major capabilities of GIS that includes data input, management, manipulation, analysis, modeling, and display output. And the current state of art platforms for analysis are with us, but we were not really aware of it. So maybe the next time you're using your smartphone, your mobile phone, you want to use it more efficiently, and you want to see how you are contributing to a certain database. Maybe as a fun exercise, you can try to do this. You can try to collect data from other users through these different platforms just from your mobile phones, which is known as the mobile GIS, and you can actually map it. So it's a fun exercise, I feel, and I think if you do it and you can come up with interesting results, you can have your own analysis about people, their movement, their behavior, their you can actually do a think map. So there are many things that you can interestingly explore through this. So this brings us to the end of this session. I hope it was useful. Since many of you are not there for today's class because it was rescheduled, I'm sure you're busy with other classes. So I will be uploading this on my YouTube channel with a link that will be updated and sent to you. So I hope when you go through this session, you will have better understanding, and you will have more comprehensive database management through the devices that you have access to, and I'm sure you will use it more productively. If you have any queries, we can forward it to the next session. In the next session, we will be talking about more progressive applications of GIS, and we will also be doing assignment 3 questions, which must have been released to you by NPTEL by now. And yeah, I hope this was an interesting session. I thank you all for your attention. We will take the questions in the next week class, which will be on Tuesday from 6 to 8 p.m. Thank you so much. I'll see you in the next class.
so proud of her daughter.